Hello, everyone. Welcome back to Codex. Today's speaker is Elizabeth Newman from Tufts University. Professor Newman is an expert in machine learning, numerical linear algebra, and optimization. Today, she'll talk about trust region gradient boosting via variable projection. Take it away, Liz.
Thanks so much, Mike. Thanks for having me, and thanks everyone for coming. I'm very excited to talk about this work. Hot off the presses, like in the last week and a half, this was released onto arXiv. It's our new work called Boosts Like a VAR Pro. So let me first give a shout out to the people who really, led this effort. The main leader of this is my postdoc, Abby. He's with me at Tufts and did absolutely fantastic work on this project. Um, and I also want to give a huge shout out to our wonderful collaborator, Deepanshu. He's from Clemson University, and he's did remarkable work as well. I also want to acknowledge the funding that helped kind of get this project off the ground. Um, so let's start with just kind of high level. What am I when I say machine learning today, what do I mean? I mean trying to learn a function f from data. So it's really a function approximation problem. And machine learning tools, learning from data, has really given us the ability to tackle unprecedented or problems of unprecedented scale before, from protein folding to weather forecasting to large language models, right? There there's so much that machine learning is enabling us to do with smart math, smart science coupled with that as well. Um, so what am I here to add today? Well, getting these machine learning models to work, it's not easy, right? There's a lot of work that goes into making these models predict what you want them to predict. And this is a process called training. And these, large models, or even small models, they are a pain to train. You often are solving this optimization problem to minimize this misfit between your approximate and target function, but it's high dimensional, maybe even infinite dimensional if you're working in a function space. You have non-convexity, stochasticity. You have to tune hyperparameters. So you not only have to solve this problem once, you have to solve it many, many times. And you don't even know if you're going to converge a lot of the time. So this is a hard problem to solve. And today's talk is all about how can we make training easier for you? How can we do it with maybe more theoretical guarantees and with a little less hassle, a little less computational cost as you go through? Our approach to doing this is going to kind of combine two ideas. We want to try to build up a nice machine learning model from lightweight models or lightweight functions. And we're going to also pair that with structure exploiting optimization. So strategic model design with smart paired with smart optimization. That's the idea of the talk today. Um, so the main ingredients that are going to go into our algorithm today, what we're going to present, are at least the first half of the talk are going to be three main ingredients. This idea of boosting, which I'll talk about, um, this notion of separability, and then variable projection or VAR-Pro. Okay. But throughout the talk, I'm going to be bouncing around kind of fluidly between two spaces, a function space F and a parameter space, which we'll think of as Rn of some sort. And our new algorithm, VPBoost, variable projection boosting, kind of bridges the gap between these two spaces to give us a unified algorithm to train the type of model I'll describe. Okay. So let's get started with boosting. What do I mean by boosting? And boosting here, really, we're working in function space. So it's an optimization in function space here. Okay. Before I go into the mathematical details, I just want to say a little bit of why people might care about boosting. In this case, I'm talking about gradient boosting. And you get gradient boosting is known as a pretty efficient algorithm. It's the stage-wise learning, and there are well-documented scalable libraries out there that one can use. It's given state-of-the-art results in machine learning competitions. It's often really designed for decision trees, though it is broader than that, but the decision tree model is where it's really been quite powerful. I mean, you get a lot of interpretability from this. And there are some known convergence properties in some cases for some algorithms here. Today's talk, we're going to go beyond decision trees and really talk about how to use boosting well for smooth weak learners. I'll talk about what a weak learner is in a moment. In particular, to handle data that might have more regularity than, say, tabular data where decision trees are really powerful. You might think about regularity arising in scientific applications where you have some smoothness on your solution that you're trying to learn or something like this. Um, okay, so let's go into what is gradient boosting. Um, and gradient boosting 101. The goal is to minimize, in our case, some empirical loss functional. So I have this optimization problem over a function space. And let me break down some of the notation here. I won't go into too much detail throughout the talk, but let me break it down at the beginning here. So we have some data from which we're trying to learn this function. And the data live in some data space. X is your input space, Y is your target space. And you have some training data, which are samples from your data space. Hopefully, this is a large and representative sample. So this empirical loss functional is a good estimate of what you're trying to fit. These are going to be finite dimensional vectors here. So when you see bold notation, finite dimensional vectors. The function space we're going to consider here is going to be L2 with the empirical measure here. So this is the loss functional we have. And it outputs into a vector space here. So it takes an inputs, outputs to a vector space. The loss function itself, so just what we evaluate for every data pair, is going to have some nice properties. So when I say it's nice throughout the talk, I mean it's twice continuously differentiable and convex in the first argument. And this is a fairly common assumption or a reasonable assumption in machine learning from doing a regression loss, classification. Both of these tasks kind of fit in this framework here. And the nice properties we have on the loss function, we're going to inherit into the loss functional as well. So this is going to be a twice continuously Fréchet differentiable and convex function. So just when I say things are nice, this is what I mean by nice. Okay, so our goal is to minimize this nice empirical loss functional. We're going to do this by imposing some practical structure on the function that we're approximating. In particular, we're going to, instead of trying to optimize over all of function space here, we're going to assume our function that we're optimizing is built as an ensemble, an additive ensemble of weak learners. So I'm thinking about my function f at maybe stage m of my training, capital M, is the sum of these lightweight functions h. And you can think about this as if f is a high degree polynomial, the h's are monomials, right? So they're lightweight functions here. And then the gradient boosting aspect of this is that we're going to optimize our weak learners in a greedy fashion. So we're going to find the next element of our ensemble that will minimize the loss functional kind of at our current ensemble plus the new weak learner. And we're going to kind of search over a subclass of functions in this case. What I gave away the punchline here, but one thing we can say is that you can think of H as a descent direction. It's in function space, it's a function that decreases the value of my loss functional. And a good choice of that might be something like the negative gradient. So that's where this term gradient boosting comes from here. Okay. So let's build a little intuition into this. I'll throw these pictures up a few times during the talk. But in kind of stage 0 or stage 1, however, if you're a Python or MATLAB person, depends how you count. We're trying to minimize some loss functional, trying to find a weak learner in our first class to minimize a loss functional. So we have this sort of function space. We're trying to get to this target here, and we're only allowed to search over the blue set, and we get as close as we can. Again, just a cartoon, I can't really draw function space, of course. Um, After we've done the best we can at this stage, we try to fit the residual here. But notice that the target changed. So I'm now trying to fit this residual, and I'm also looking at maybe a different class of weak learners here. But I still try to make progress at this next stage, and so on and so forth. Okay. Um, so, and you can always look in the same class, but the target changes each time. What you might see is in one way to visualize intuitively what might be going on here is that you can think about if we're trying to approximate this function over here, that each week learning stage maybe is learning higher and higher frequency information, fitting higher and higher frequency components. That's not, it doesn't, multi-grid is more formal in this regard, but it has kind of a similar flavor of what these weak learners, what we might expect them to do as we learn. Okay. Um, so that's gradient boosting 101, some intuition. What are we actually going to do? Well, the original problem is we're trying to solve this optimization problem for our weak learner, and it's still a hard problem to solve potentially to search over function space. So what we're going to do is we're going to build a quadratic approximation about our current ensemble. So just a Taylor expansion. Again, this is why we want a nice loss functional so we can do this. Just to clarify notation quickly, what do I mean by this inner product? I mean the L2 inner product under the empirical measure here. So just an inner product per datum, and then you take the average of those. And a similar thing for the Hessian. I'll show that a little later in the talk. And then coming all together, what we're trying to do with boosting is we're gonna actually minimize this quadratic functional, which I'll denote with this QCal here. And that's kind of our weak learning problem in function space, what we're gonna try to do with boosting. Okay. Okay. So that's we're going back to our main ingredients now, but we've just covered boosting, and I want to connect the dots as we go through. But the key aspects of boosting I want to emphasize, we're looking at an ensemble of weak learners. That's the structure we're imposing in function space on our model. And then we're going to make the optimization problem a little easier to solve by doing an approximation of our loss with a quadratic functional. Okay. And this is a well-known boosting technique. Some of the state-of-the-art methods out there really do this quadratic functional approximation. Okay. So we've worked with boosting, but we have to actually get this onto the computer, figure out how to solve this. And the way we're often going to do this is through parameterization. So how are we proposing to parameterize, in particular, our weak learners, so that we can use kind of numerical optimization to solve for these? And this is where the idea of separability comes in. Okay. So a separable model, what do I mean by this? I mean it's a nonlinear featurizer followed by a linear mapping. And the way I'm going to write this mostly in the talk is as this matrix valued function A parameterized by theta. So A theta is our nonlinear featurizer. And some linear weights W here. So again, W are the linear weights. Our nonlinear featurizer takes in data and some parameters, outputs a matrix here. And so we say this A lives in a Bachner space, a matrix valued function, space of matrix valued functions, and we'll assume it has just the operator norm on it. So nothing weird with norms in this talk, but they are important that the different spaces do matter here. Where does separability arise in the wild? Well, you might have seen this picture on the first slide or on the slide before, and this is what's known as a quasi-matrix. So you can think of maybe one dimension is continuous and then the other dimension is finite. You could interpret this separable architecture as in a quasi-matrix way. because A is really like every column could be a function in some sort of in some sense. The other way that we'll use a lot in our numerical experiments is in deep neural networks. You see this. So you have some neural network, you kind of collect everything before the final layer, call that a nonlinear featurizer here, and then you have some final linear weights. When you write the neural network down, this W times featurizer, you can vectorize your weights, and you can have this structured matrix as your operator, as your nonlinear featurizer here. So we're collecting quite a few possible frameworks with the separable model. It doesn't have to be a deep neural network. It doesn't have to be a fully connected neural network. It can be a whole, anything where you sort of have this final linear layer here. Okay. So what makes this model so nice when we pair it with boosting? So let's see how these two things come together. Okay. So second order boosting and severability. Let's go back to our quadratic approximation of our loss functional about the current ensemble. And let's assume now that we have the structure of separability. So let's plug in that separable weak learner here. Everything's nice and inner products kind of you can play with them the way you expect. So we can actually kind of let me do that one more time. I can move the A, like kind of take the transpose and move it onto the other side of the inner product. And I can do something similar with the Hessian with both A's here. So that's this step right here, just group moving the A's off the W's. That's the benefit of separability. And just to give you a sense of what these things are, again, this is kind of an empirical inner product where you evaluate all these functions at the datum and average here. So this is actually a matrix that you're building. And then this is a vector that you're building, a finite dimensional vector. Okay. What's nice about the separable model is this is all equivalent. I haven't changed anything, but I now can think about the second order problem with separability as a function in parameter space. So this is now a function Q that's some quadratic term in W and some linear term in W. And the connection of function space is that this quadratic functional evaluated at a separable model can be equivalently represented as a quadratic function. In a quadratic function in W, I should say. It's non-quadratic in theta. Okay. So let's put this together here. We started with boosting in function space. We built some structure on the types of functions we were going to learn. And we also looked at a quadratic approximation of the optimization problem. We've added some structure to the weak learners themselves as well. We've made them separable. And this is not such a restrictive structure. It's quite common, but we've explicitly encoded this. And this meant we had a way of writing this quadratic functional as a quadratic function in W here. Okay. So the last step of our algorithm is to see how can we take advantage of the structure? How can we optimize this quadratic function in W smartly? And this is where variable projection comes into play. So let's look at variable projection VARPRO at a high level here. We are trying to solve an optimization problem where we have two weights, W and theta, and it's some objective function J. I'll be specific about what this is in a moment. We want to use some structure exploiting optimization here. In particular, we want to leverage the fact that we know there's linearity in W in our case, or some nice structure in W, and there's a nice coupling between the W and the theta. If I pick a theta, I kind of know what a good choice of W is. So how do I take advantage of this? Well, the VARPRO formulation is to build this reduced optimization problem. So we have some reduced objective function that only depends on theta. And this is your full objective function evaluated at a specific choice of W. So when you see it's this W star of theta. So W star of theta is a function of theta, and it's the optimal choice of linear weights for a given theta. So we achieve this through partial optimization here. But it really is the VARPro mentality is that this W is really a function of theta. It's not an alternating method. These are now really coupled, tied together here. So just to give you a little visual of what's going on, let's say this is our objective function here in the gray, in black. And we're trying to get to this star here. What VARPro does is it is going to choose the best choice of W for a given theta. So fix theta, move across the image where you see the darkest color, that's the lowest value, and that's where the optimal W is on this yellow path. And we kind of call this the yellow brick road of optimization to get you kind of follow the yellow brick road to get to the minimum. So the VARPro is just going to follow this path, this kind of manifold, to get to the minimum here. A gradient descent would maybe zigzag somewhere out here. VARPro immediately comes on along this optimal path. Okay. So why is VARPro, what makes it so great for optimization in general, and then what makes it special in our case? So VARPro has some quite nice theoretical properties. It has both first and second order properties that make it a nice choice of optimizer for this kind of coupled variable problem. The first thing is that the gradient of the reduced objective is related to the gradient of the full objective function, as long as we evaluate at the optimal W. So this is actually not a one-line proof. If I try to take the gradient of the full objective function at this optimal W, I have to differentiate through W star now as a function of theta. So I get this chain rule coming out here. But because we've optimized W, this first gradient here is equal to 0. So we get to eliminate this term. We don't have to differentiate through the optimal W anymore. And we wind up with just the gradient that we might expect. So from an implementation standpoint, if you're using gradient information for theta to optimize theta, you can throw VARPro on top. You don't have to think about it too much. It also has some nice second order properties, namely the reduced Hessian is related to the full Hessian through a Schur complement. So don't worry too much about this notation, but what this means is that the conditioning of the optimization problem in the reduced space is no worse than the conditioning in the full space. You've made the optimization problem nicer and easier. Okay. Let's look at what VARPro looks like for boosting. So let's go back to the boosting problem here. So we have a specific objective function where we have our quadratic function in W, non-quadratic in theta. And what we're going to add in is we're going to add in a little regularization here. In particular, Tikhonov regularization on the W. I'm not going to be explicit about the regularizer for theta here. Okay. We've built our reduced optimization problem just like we did before, but we actually noticed something quite nice. This function again is quadratic in W. So closed form solution, an analytic solution for the optimal linear weights for W star. So W star of theta is just this just this of this form, your Hessian that depends on theta, plus your Tikhonov regularization term, inverse times your negative gradient that depends on theta. But I want to make a key point here. This closed form solution did not depend on what loss functional we were using, as long as it was nice and at least right now we're assuming convexity, right? So in the past, when you use VARPro, you get a closed form solution for quadratic loss functions, but not for using VarPro with, say, cross entropy or other losses. Here, no matter what loss we're using, we get a closed form solution for the optimal linear weights in this boosting framework. It's kind of beautiful how these things came together. Okay, so let's just bring it all together here. We looked at these three ingredients that go into our new algorithm, variable projection boosting, VPBoost. So it's a combination of boosting, separability, and VarPro, bringing structure and function space to the weak learners and choosing a smart optimizer. This is what's all going to coalesce into VPBoost here. So before I go on, are there any questions? Because there are a lot of ingredients here that come together. And if not, that's totally fine. There'll be time for questions at the end. Okay.
Sorry, yeah. So
Yeah.
when you're, I guess like the kind of the cool thing is that once you find theta, W star can be done exactly. But does it matter what sort of algorithm you're using to update the thetas at each step?
Great question. We'll go over a specific one in a moment, but as long as you're only using first order gradient information, then it does not matter. Um, it if you want to go second order information to update theta, you can do this as well, but you have to think a little bit more carefully about differentiating through that W star of theta. Yeah.
Okay, cool, thanks.
Yeah. Okay. Um, so as much as I've been going over these ingredients, I haven't actually told you what VPBoost is yet. So let me do a quick little let me just mention that this framework does exist, or what makes this different than the existing works, and then I'll talk about VPBoost in a second. So don't worry too much about all the details in the table, but there's a lot of literature out there about decision tree boosting, and we call it neural network boosting, but it could be more general here. Um, but some places they do have this idea of separability or this idea of linear weights, at least in the neural network context. But most of them either they optimize the linear weights after the fact, or they do it before they even start training. And we really integrate this into the optimization. We'll talk about why that's valuable here. And then there also are a few methods that use second order information here, and there are slightly different ways to build ensembles. So when we do this additive approach, so it really is the stage-wise learning, which has some efficiency benefits. But some of the other compositional or structural ones might be more expressive in other ways. So there are a lot of different tools out there. But we are, to our knowledge, we're the first to really bring together the second order optimization with this integrated approach to optimize the linear weights here. But there are some, excellent methods on this table. Okay, so variable projection boosting, VPBoost. We have these three ingredients, boosting, separability, and VarPro that come together. What does the algorithm look like? And it's really two algorithms in one. You need to know what you're doing at the weak learner level in parameter space. How do we actually update the thetas? And we have to know what we're doing at the ensemble level, right? How we're actually building this function approximator. So at the weak learner level, it's no secret we are using VarPro. We build these what we call the reduced gradients and Hessians, and then we update theta with just some gradient direction here, where the optimal linear weights. And the optimal linear weights, again, have this nice closed form solution. We do this for as many iterations as we like, and then we return some weak learner at some terminal iteration, capital K. Okay, so nothing too this is pretty standard optimization, other than we make sure we're using VarPro here. The next step is you take this weak learner level learning, right? And you have to take that weak learner and you have to add it to your ensemble and be smart about how you do this. So I want to talk about this connection, spend a little time here, and then talk about what we actually do at the ensemble level. Okay. And there's kind of some crucial theory that really helped us see how these things were connected. The first one of our early lemmas that we were able to prove is that if you use a VARPro weak learner, so a separable learner with optimal linear weights, you actually guarantee you have a descent direction. And it's again a one-line proof written on 3 lines. If I just go by the definition of this inner product, I expand, I see this reduced gradient show up here, so I can pull that, I can group that all together, kind of factor out the W star that does not depend on capital N or does not depend on I anymore. I can then write down the definition of what W star is, this closed form solution. And what I see here is this negative kind of inner product with this symmetric positive definite matrix in the middle. This is negative. So just by construction, we get a descent direction. We get a good direction to update our ensemble to decrease that loss functional just by choosing those optimal linear weights. So this was quite exciting to us, even though it's a short proof. We said, we think we're onto something here. Like this feels like it's pairing the right way in this space. So we want to understand a little bit about what VARPro is doing and how it really bridges between function and parameter space here. So this picture, there's a bit going on here, but what I want you to look at is in the parameter space, this is the picture you saw before, where we're just in VARPro land, with VARPro, we're optimizing along this curve. And every color you see here is a new update of the theta. Every time I update theta, I still am staying on this optimal linear weight manifold. Okay. So every color you're seeing is an update of theta. This is at the weak learner level, right? What is simultaneously happening in function space because of this descent direction tie-in, what's simultaneously happening is at a particular stage, so at a lowercase m at this stage, for a fixed theta, we have a linear subspace where we search for the best weak learner. We find this, and then the linear subspaces evolve in function space simultaneously with how these parameters are evolving in parameter space. So VARPro is kind of keeping these two tied together, and it guarantees that as I make progress along this optimal linear weight curve, if I make progress along here in parameter space, I'm also making good progress in function space. Like just tying these two things together. Okay. So we're excited. VARPro seems to be giving us the right good directions to go to update our ensemble. But there's a little bit more I want to go through before I actually tell you what we do at the ensemble level. And it's sort of we need to figure out how to control the contribution of each weak learner. Descent's not enough, right? In standard optimization, just having a descent direction, you could step too far or you could step too little, right? You want to have the Goldilocks step just right. And you might see this from line search methods or other techniques. VPBoost, this ensemble level update, these optimal linear weights, really lend themselves to a trust region perspective. So I want to talk about this a little bit as well. Okay, so just rewriting this, the closed form solution for our optimal linear weights is of this form. Recall this came from being the minimizer of some Tikhonov regularized quadratic function. So I'm just writing this in terms of W here, but that's where the optimal linear weights came from here. And it turns out a Tikhonov regularized quadratic problem can be reframed as a constrained optimization problem. So you have some quadratic objective subject to some constraint that the norm of your weights isn't too large. Visually, what this looks like is if this is our W here, we're building some sort of region of trust. We take a step in that region, and then we update from there. We circle it, do it again and again. So this is the kind of this delta here is your trust region radius. It's that circle coming around here. And so this Tikhonov regularization that's controlling the norm of the weights, it can alternatively be controlled by a constraint here. And I know this constraint looks a little funky. You'll see why on the next slide, why we write it this way. I want to make a quick point here that there's a key relationship between the trust region radius delta and the regularization parameter. Namely, they're inversely proportional, and there's actually a one-to-one relationship if lambda is greater than 0. In the language of constraint optimization, lambda is your dual variable here. So in our case, it makes a lot of sense to think about this regularization parameter. It's directly what goes into our closed form solution, but it has this nice connection to the trust region radius of more traditional trust region literature. Okay. So I didn't do anything new on this slide. I just said our optimal linear weights can be reframed as a solution of a trust region subproblem here. Okay. So in parameter space, we have this trust region method for W, and we use varpro to solve this, right? So we have our quadratic function in W. We can then use a nice relationship of submultiplicativity to relate the weak learner, the separable weak learner, to the trust region constraint. So we can use submultiplicativity of norms, and then we get this relationship where the product of the norm of the featurizer and the optimal linear weights is precisely this trust region radius. And we can do this because we're going to assume we have some non-negligible regularization. So lambda is positive here. Okay. So what does this connection allow us to do? It allows us to relate a trust region bound on W, so this trust region bound, to a trust region bound on the weak learner itself. Hence, in function space, the varpro weak learner satisfies a functional trust region method, namely our quadratic functional over these separable learners bound subject to this trust region bound here. So in the punchline here, the punchline is that VPBoost, variable projection boosting, is a trust region method in function space. And there are a lot of benefits to this. If the optimization is difficult, the trust region method will not let you take too big of a step without, it'll kind of protect you from bad steps. It also allows you to automatically adapt some hyperparameters. There are mechanisms in there. So trust region methods can be quite appealing for these hard optimization problems in machine learning. Okay. So let's get back to our VPBoost algorithm. It's 2 algorithms in one. Weak learner level is varpro. At the ensemble level, we're doing a functional trust region approach. There are 2 things I want to tell you about trust region approaches. The first is that most of the decisions that, at least at a basic trust region approach, come from this reduction ratio row. That's looking at how you have your weak learner you're plugging in. You want to say, okay, how much did that decrease my loss functional, the thing I care about, versus how much did it decrease the quadratic model, the approximation that I optimized for? And this ratio is telling you whether you should accept or reject the weak learner, whether this update is good for you. That's what this ratio is telling us. Once you compute the reduction ratio, you have this accept reject step, and you also have a mechanism to adapt your regularization parameter. So there's this user-defined cutoffs that tell us whether we don't reject the weak learner and start over, or we accept it, we update our ensemble and move on from there. And we also have a mechanism to control the regularization parameter here. So this is, you can think about increasing the regularization parameter as we took too big of a step. We trusted our quadratic model too much. So we have to increase the regularization parameter to not take such a large step. Okay. In a sense, we're penalizing the norm of the linear weights. We don't want those to be so large in the future. Okay, so that's trust regions in 2 steps. There's always more detail to do here to go over here, but hopefully that's there's a lot that goes into this algorithm. Okay, so the other thing I want to mention though is once we're in this trust region setting, we can now actually use trust region theory to talk about convergence. And the key to all of our theory is to mine this submultiplicativity gap. So we have this trust region method in function space. We're relating it to a trust region method for W in parameter space. But there's this gap that came from submultiplicativity. So we just needed to, in our theory, we needed to address this gap with some reasonable assumptions. And then we were able to really use all of that trust region convergence analysis here. So the assumptions that we put on here are that the derivative information in parameter space, this G and H, it has to retain enough of the right information from the derivative information in function space. And it's actually all about proportionality, so it doesn't have to retain exactly the same information. It just has to make sure that we're moving in the right direction quickly enough. We need a few additional algorithmic assumptions, like our featurizer can't become arbitrarily large or small, which seems reasonable. You want there to be information in that featurizer. And we want to make sure we have a non-negligible regularization. Once we have these 2 assumptions, we actually get convergence guarantees. At the ensemble level where we're actually trying to learn, we converge to a stationary point under quite mild assumptions on our featurizer. In fact, our assumptions are prescriptive. We can tell you if you're making progress at every stage of weak learning. This is actually a bit different than the literature. I'll talk about this on the next slide. We also can get a convergence rate. We can get superlinear convergence. We need stronger assumptions on our featurizer A. And the stronger assumptions we see similar types of techniques in the literature, but they sort of break the idea of these being weak learners, not too large. So we get this, but there's a trade-off here. It's sort of up to you how you like to view that kind of result. Okay, so in the literature, we're looking at the theory now, same methods, but the theory. What you see in terms of convergence is you get or in terms of just results, you get things like converging to a global minimizer or getting some sort of generalization bound, how far off you are. Do you overfit or do you generalize to other data kind of in a statistical way? Ours is really about converging to a stationary point, so a slightly different result. And part of that is that we're making assumptions per weak learner. Many of these other methods make ensemble level assumptions. Do I have weak learners that are dense in my space, in the function space? That's where this MCA, this minimum cosine angle condition, comes into play. So there's a difference in how we describe theory, but ours is much more about how do we actually construct weak learners under some of the restrictions that we have, like separability and the fact that we have to retain proper derivative information, which is fairly easy for us to satisfy, but something we have to actually prescribe here. Okay, let's do some results for the last 5 minutes or so. So I want to start with a few toy examples that I think will illustrate the potential of this type of technique. So we're going to try to fit a 2D function. So we have an x and a y input, or x1, x2 input, and we're trying to fit this highly oscillatory function that you saw earlier, actually. And when I say a weak learner, I'm thinking about a neural network here that has like, on the order of 50 to 60 parameters. So in the blue, very small neural network. And and we're building an ensemble of networks of this size. It's a small problem as well, but that's the idea here. Okay. So just to show you a little bit about how the training goes, I'm comparing blue is just not using VarPro, but doing gradient descent boosting. The red is using VPBoost, and XGBoost is in black. It needed, in order to kind of match the capacities of the learners, it's hard to match these because XGBoost is a decision tree, kind of state-of-the-art decision tree method. So we gave it a slightly different number of learners to try to make a fair comparison. And you're just seeing kind of the final loss from that. And what you'll see in a few results here, but we see that VarPro really converges quite nicely compared to gradient descent. The VPBoost is really doing great at the ensemble level. And in terms of how well we really care about how this validation loss looks. We're going down nicely. We outperform XGBoost in this regard too. So that's sort of our during training. That's our way of measuring: are we overfitting or are we generalizing well? This gap between the black lines is indicating that XGBoost might be overfitting a bit in this problem. Okay, so let me show you what this training looks like here. So again, here's our ground truth. This is where we start with a constant approximation with one learner apiece, and they all start with the same constant. As we learn, as we add learners, you'll see we're capturing higher and higher frequency information. The gradient boosting really stagnates pretty quick because there's this strong coupling between the W and the theta, the two blocks of weights. And we see that as we get up to 10 learners, 11 learners, XGBoost was given 41, but there's a reason for that comparison. But VPBoost and XGBoost are capturing the different frequencies. You see with the decision tree, it struggles to capture kind of qualitatively the smoothness of this function, whereas VPBoost is really starting to capture that well. So this is the regularity we're talking about. So both numerically and qualitatively, it seems like a neural network-based approach was appropriate for this data. We also looked at things like classification problems, so non-quadratic loss functions. Here we're looking at the Swiss roll, so we have a red and a blue class kind of intertwined here. And we used a slightly smaller weak learner and actually an even smaller ensemble. This was it was a pretty easy problem if we made our learners much larger. Training looks excellent for VarPro again. VPBoost looks great. XGBoost really struggles with this one in particular. And let's just show you some results here. I'll get to the end here. If VPBoost does quite nicely capturing that spiral, capturing both the red and the blue. XGBoost needs way more learners to refine this space because of because of the structure of the Swiss roll really struggles with this type of framework. We did something similar. I'll skip this one for a moment. We also looked at some higher dimensional examples. So we looked at things like MNIST classification, a PD surrogate modeling example, and a computational physics example that's more kind of a benchmark in decision tree boosting literature. And in all cases, we were able to get the lowest loss on what we trained, which was what we trained on, and the higher, a different metric that we were able to get higher compared to the other methods here. So we were quite excited about these results. I also want to mention that for this PD surrogate modeling case, which has a lot of smoothness under the hood, the decision tree method did not work so well for this one. It works quite well for tabular data, like this Higgs data set, but we were actually able to achieve some nice improvement on that. And I'll mention all of these methods we tuned with Optuna. We tried to give them their best chance while keeping the capacities somewhat comparable here. For this, just a quick look at how fast this is, because variable projection is a little more costly than just doing a gradient-based approach. And we see for different scales of problems, we do achieve some speed up to get to the same loss as the gradient descent case. So to get kind of the same level of fit, we can do that in less time with VPBoost for various output dimensions here. So this was great for us to see as well. I'm happy to go back over this, but let me jump to the end here. So just a quick recap. We talked about the three ingredients that go into VPBoost: boosting, separability, and VARPRO. And these are all designed to help us train better, with lightweight models and with smart optimization here. We were able to get a closed form solution for those linear weights for many different losses. That's kind of leveraging the function space connection here. Working in a function space, we got some nice structure. VARPRO connects function and parameter space nicely. We were able to express this as a trust region method and get some convergence guarantees, and we saw some empirical success here. Going forward, we really want to scale this up, see if we can accelerate it even further, and maybe thinking about how to turn this into a stochastic variant. So with that, I'll just mention our paper is on arXiv. Please take a look. It just came out like within the last 2 weeks, maybe less. Thank you so much for allowing me to speak here and share this. I'm very excited and happy to take questions, or feel free to email me after the fact as well. Thanks, everyone.
Thank you. All right, let's see. I'm going to click buttons, which is how we say thank you for a nice talk on the internet. I encourage everyone else to click those buttons too. And then I guess I have to hit end recording. Stop.